Hello, good afternoon. I'm Sammelan. I'm from University of Nevada, Reno, and a Ph.D. candidate there. And I'm doing this research under the guidance of Dr. Mohammad Mustafa. Uh, I would like to thank my sponsors and my material providers, New Mexico Department of Transportation, who is sponsoring my project, and a special thanks to Transpo and QuickBond for providing all the necessary material for my project. So the presentation outline is introduction, experimental program, selected results, and concluding remarks. At this point, I guess introduction isn't much necessary for polymer concrete. So as you all know, polymer concrete is a non-cementitious product with all different type of polymers that we have been listing this whole afternoon. On the right, which that may be more interesting, those two are one of the resin and hardener of one of the product that I'm using. It's a polyvinyl ester-based polymer concrete. On the left is the resin, the monomer resin, and on the right side, that's the MEKP hardener. So on the application part, the application on the left side is explained a lot, has been discussed a lot in this session. But for this application, I want to focus on the application on the right side, which is the structural application. On the top, it's a bridge deck joint, and on the bottom one, it's a 3D printed bridge, a segmental bridge, which is joined using polymer concrete. Not that bridge, but the one that I'm testing. That's just a representation of a 3D printed bridge. So why polymer concrete? At this point, I don't think I need to explain this a lot. Okay, so the research motivation on the thermal aspect. So these are two of the large-scale structural tests that we are doing at University of Nevada, Reno. On the left is a full-scale or a large-scale bridge deck joint. It's 10 feet by 8 feet. And we are testing for the longitudinal joint here, as you can see here. And on the right, it's a 3D printed segmental bridge. The segments are made up of regular concrete, but the joint is made up of polymer concrete here. So these are one of the major applications that we want to target. But the research that I'm presenting today is a precursor to these research on the material level, on the material level. So what motivated this research is, as you know, the thermal variations throughout the years, the seasonal ones and the daily ones. For the polymer concrete, the thermal variations can have two kinds of effect. One is due to the mismatched coefficient of thermal expansion between the polymer concrete and the regular concrete, because since those products are used in the joint, coefficient of thermal expansion is important. And on the other hand, due to the material degradation of polymer concrete because of temperature, there can be reduced performance. So we wanted to capture these two effects in our research. So the objective was to study the mechanical and bond behavior of polymer concrete under thermal stresses. For our research, as I already mentioned, we were looking at the material level, at a component level, and a structural level. We were not able to perform any thermal test on the structural level itself, but we did perform on the material level and the component level. So for this research, we used two polymer concrete. One is methacrylate polymer concrete, PMMAPC, which I have been, that's the acronym that I have used throughout, and polyvinyl ester polymer concrete. These PCs were used as recommended by the manufacturer. The resin, the aggregate, as well as the mix was as recommended. There wasn't any mix design performed on it on our part. We used as it is. And the materials, like those two polymer concretes, were selected based on a prior research where we did a comprehensive study, comparative study of 6 different types of polymer concrete, and we found these two to be one of the better ones. So we went with these two for our for this part of the research. So before studying the thermal, thermal behavior, the two prime reasons why you are doing this, the coefficient of thermal expansion and the glass transition temperature. We measured the coefficient of thermal expansion as shown in the right with a comparator at different temperatures. We used 23 degrees Celsius to 100 degrees Celsius as the temperature range, and found that polymethyl methacrylate polymer concrete has a coefficient of thermal expansion of around 3 into 10 to the power minus 5 millimeter per degree Celsius, and polyvinyl ester had 2.15 per degree Celsius. For reference, regular concrete has a coefficient of thermal expansion of 1 times 10 to the power minus 5 in the range of 10 to the power minus 5 millimeter per degree Celsius, which means polymer concrete has a coefficient of thermal expansion of 2 to 3 times the regular concrete. And the glass transition temperature, we did a test for both of these. These results, the 66 degrees Celsius and 60 degrees Celsius, should be taken with a grain of salt or a grain of sand, I guess. As Mr. Stenko told us earlier, in the PMMAPC, the resin, we didn't have a different hardener. The hardener was already mixed with the fine aggregate or the sand. So the product that we used for testing the glass transition temperature wasn't a pure polymer resin, but a scrap from the concrete, which may have included sand and other impurities with it. So we are not comfortable that this is the glass transition temperature of the resin itself, but this is the glass transition temperature that we obtained from a scrap that we got from the polymer concrete. Now on the thermal cycling part, as you saw, the glass transition temperature is somewhere around 60 degrees Celsius. So we wanted to do 2 thermal cycling. We did 10 cycles between 0 and 55 degrees Celsius, and 10 thermal cycles between 0 and 110 degrees Celsius, which are denoted as T55 and T110. On top of that, we also wanted to see the behavior of polymer concrete on extreme negative temperature, which is minus 25 degrees Celsius. So we had 3 thermal conditions. On the right side, I have shown one of the thermal cycling, which is T55. A similar cycling was done for 110 degrees Celsius. And for the minus 25 degrees Celsius, no cycling was done. The concrete were tested at minus 25 degrees Celsius itself. For those T55 and T110, the cycling was done, and the residual strength was measured not at 55 degrees Celsius, but at room temperature after exposing to those cycles. So these are some pictures. These are some samples from the oven, and to get a 0 degrees Celsius, ice and water mix remains at 0 degrees Celsius. So we plunged that concrete to ice water mix directly. We want to call it thermal shock, as we directly plunged the specimens from oven to the water, like ice water mix, instantaneously without letting it cool down. So for the test sides, we did 4 different type of tests. One is the compressive strength, the regular compressive strength and modulus of elasticity, the flexural test, and we also did 2 more tests on the component level, that is the bone test. On the third figure, you can see a pull-out test being performed from a block of polymer concrete. It is number 4 rebar, grade 60, with 8 times the diameter, which is 2 inches, embedded inside the concrete. We found that 8 dB was sufficient in case of a regular specimen in a prior research which we used here. And on the fourth, here we can see a cylinder. That cylinder is made up of, the half of the cylinder is made up of conventional concrete, and half of that cylinder is made up of polymer concrete. The conventional concrete wedge was first prepared, and then we used a sandpaper to remove the debris or dust from the surface, and poured polymer concrete into it to test the bond between conventional concrete and polymer concrete. So all of these specimens were tested on those 3 thermal conditions, and a baseline test was also performed. Actually, 2 baseline tests were performed, because one of them was performed at 7 days, and one of the baseline test was performed at the day when all of those specimens were actually tested after thermal cycling. It took around, like, to figure things out, around 5 months. So the baseline tests were tested at 7 days and at the age of around 5 months. So on the compressive strength side, this is a compressive strength for polymethyl methacryl polymer concrete. I want you to focus on the right side. As you can see, there isn't much degradation when subjected to both 55 and 110 degrees Celsius. On the extreme negative temperature, the compressive strength increased significantly. Similarly, for polyvinyl ester polymer concrete, you can see 2 reference lines there. I thought polymer concrete wouldn't increase, there wouldn't be any increase in compressive strength, late increase, but you can see the difference between the dark line and the dotted line. Polymer concrete still gains some strength even in late ages, although we say that the reaction is instantaneous. And on the thermal part, there is no degradation in compressive strength, and in the extreme negative temperature, there is an increase in compressive strength. But here on the stiffness side, as you can see, although there is the compressive strength remains same, the slope is decreasing, which means the material is losing stiffness when subjected to thermal stresses. I forgot to mention that in the earlier slide. The same can be seen here too. Like in the T110 cases, the material is getting flexible or is losing stiffness. Now, I have summarized that as modulus of elasticity here. As you can see, for T110 and even for T55, the modulus of elasticity is decreasing from the baseline value or the reference values. Now, going on to the flexural strength, a similar kind of situation can be seen. The stiffness is decreasing, and the flexural strength is almost the same. Not much different, but the stiffness is decreasing. And the cold condition or extreme cold condition is increasing the stiffness as well as the strength. Now, the bond with rebar also didn't change. The temperature conditions did not do much to the bond with rebar, except for 110 case where there was a minimal drop in bond strength or the maximum rebar stress in case of PMMAPC. Now, the interesting results come here, where this is the result of a bond test between polymer concrete and conventional concrete. The solid line and the dotted line are the benchmarks that we defined of the same set of categories or the same test performed without the thermal samples or the baseline test. So, as you can see here, we performed the test with primer and without primer. This is the case for polymethyl methacryl polymer concrete. And for T55 case, there was a little bit drop of bond strength, but the bond strength was still above the baseline test at 7 days. But at T110 condition, which is the thermal cycles between 0 to 110, there was almost a complete loss of bond strength between polymer concrete and regular concrete. That is with primer. Interestingly, without primer, the same material did better in case of T100. It wasn't as good as the reference condition, but it was still better than the one with primer. Now, for polyvinyl ester polymer concrete, we saw an opposite result. The cases with primer had better retention of bond strength, but the case without primer, there was a loss in bond strength for T55 and almost a complete loss in bond strength for 110 degrees Celsius. So the preliminary conclusion is, although the material strength or the material properties are retained at like extreme thermal variations, but the bond strength with conventional concrete can deteriorate when we subject it to such extreme thermal variations, and that should be considered in the future material development of this kind of polymer concrete. To continue our research, as I already told, I am using that product, these kind of polymer concrete for large-scale structural tests. I have already completed most of my structural tests, and I'm analyzing those results right now, and we are planning to develop at least some design guidelines to support New Mexico DOT on this, on the implementation of polymer concrete. Thank you very much.